All right. Hello, everyone. Today, we're very happy to have Abhi Paul, who's going to be talking to us about addition. Very exciting. So please take it away, Abhi.
Okay, cool. So as was announced, I will indeed be talking about addition. In particular, I'll give an elementary introduction to addition with carrying. I'm assuming this is familiar to most of you. You have probably done this, 2 decades or earlier. But in any case, I'll see if there's something interesting there. But before that, I wanted to give like advert that all of you should come to the town hall that's happening like later today. Of course, we'll be sending out more emails, but I felt it was necessary to encourage everyone to come. This is extremely important if this was not clear, because the bargaining process really affects how we work as TAs in the department and how we just interact with the university, and if you are compensated fairly for what we do. So I think it's extremely important that you come, and you should come, and you should encourage others to come as well. Okay, so that said, let's actually begin with the talk, and I will give some examples of how do we add, and how do we add with carrying, and how do we add without carrying. So without carrying, maybe we want to start with our favorite prime number, say 57. And to that, we want to maybe add another number. And here, it's very straightforward, because I just need to add the units digit to the units digit, and I need to add the ones digit to the ones digit. So if I add the units digit to the units digit, I get a 9. And if I add the tens digit to the tens digit, I also get a 9. So this was easy. This was very uncomplicated when I first learned it. And then they introduced this addition with carrying, which is slightly more complicated. So we again start with our favorite prime number. And maybe you want to add like a not so favorite prime number, like maybe a prime number that you don't like as much. And here something interesting happens, because once we add 7 and 3, we get a 10. But there's only place for 1 digit here. So I can only add a 0. And then what I do is that I carry over the 1 that I had remaining. And then I pretend that I'm now adding this in the tens place. And then I do 5 plus 1 plus 1. That gives me 7. So 57 plus 13 is 70. A more complicated example, or I suppose, so in some literature, this is just considered a degenerate case of carrying. Oh, that is very interesting. Yeah, I don't know what Paul is referring to, but yeah. Anyway, maybe he can explain later. So this doesn't just happen with usual addition. Like we do more interesting forms of carrying in other scenarios as well. So for example, maybe you're going to listen to me for 0 hours, 45 minutes. I'll just go on and on about carrying. And then maybe you want to spend 30 minutes at the Art of Espresso Social, doing whatever you do at the Art of Espresso Social. And you want to see what is like a total time commitment in this entire business. And now if we add 45 to 30, we get 75, but 75 is greater than 60, which is 1 hour. So we just look at 75 mod 60, we keep 15 minutes here, and we carry over 1 minute. And then we just say, oh, this is 1 hour, 15 minutes. So my goal today is to see exactly what's going on here, because really what's happening is that there are 3 structures at play here. There's addition that's happening in the tens place. There's addition that's happening in the units place. And both of these things are related by this carry operation. So somehow some structure here and some structure here together with the carry gives rise to some structure, some larger structure. And just to explicitly point these things out, this structure is the structure of usual addition in the units or ones place, The second structure is that of addition in the units or tens place, or in the tens place, sorry. This is the second structure of addition in the tens place. And finally, these 2 things combine to give us the usual notion of addition. So this is the usual notion of addition. So this is the usual addition of two-digit numbers, two-digit numbers. So the first question that I want to answer is that what is a carry anyway? Like, can we define this in sort of a more precise way? And to do that, we will give some names to the things that we are considering. So first of all, usual addition is happening in the group Z mod 100, which I'll call E. The addition in tens place is happening in Z mod 10, because I can think of this as, adding 0 to 10 to 20 to 30 and so on. And this group I'll call T. And really, this group has like a nice relationship with my group E in that it is a subgroup of E. And there's a very natural way in which I can think of the tens places sitting inside like two-digit numbers. And the addition there is consistent with the addition that we usually do. And then there's this other group, units place, which as a group is, again, isomorphic to Z mod 10. But this has a different relationship with E, because it doesn't make sense to think of the units as a subgroup of E, because they keep repeating. So maybe it's better to think of this as the quotient of E by T. And this is not too bad. This is not too bad, because we see that if I have any x in E, then the units place, so then the ones place or the units place of x is given by the coset x plus t inside my group U. So this is a reasonable sort of setup to work with. And now in this setup, what a carry is something that takes two units and gives me back something that is in the tens group. So this is what a carry is. And I will denote this by a Z because there's this long tradition, or I suppose accident, that many things are named after German words. So I'll call this Z because the German word for carry is Zehner Übertrag. The actual spelling doesn't matter. Übertrag. So that's why I'm calling this a Z. Okay, so that's what a carry is. And one thing that is very obvious to us, because we have been working with the usual number system for so long, but that I would want to explicitly write down as an observation, is that anything in my group Z mod 100, which I was calling E, has a unique representation in terms of the place value system. So in other words, if I have any number, I can write it as a ones digit and then a tens digit. And now I can define addition operation in E using the additions that I have from my units and my tens. And the way I do it is that I say that, if I have two-digit numbers, the units digit is just the sum of the units digits of the two numbers that I started with. But the tens digit is a bit more complicated. So first I have to add the tens digit of the two numbers, and then I have to add the carry that I get from looking at the units place. And this is and note that this sort of completely gives us whatever structure E has. Okay, so if we start writing down values for Z, because this is just a function from U cross U, we see that E takes these values. This is the usual notion of carry. So before I generalize this, I would like to sort of write down some other properties that E must satisfy. So of course, we want our addition to be associative. So we want this usual identity to hold. And now let's try to write this in terms of my addition. So on the left, addition with carrying. So on the left-hand side, we'll have A1 plus A2 plus Z B1, B2. The units place is kind of irrelevant for this discussion for now. And to that, I'm adding A3, B3, and this just gives me A1 plus A2 plus A3 plus Z B1, B2. And now we have to add this other carry that is coming from B1 plus B2 and B3, which is B1 plus B2, comma B3. And again, here I get V1, V2, V3. And we can do something similar on the right-hand side. But for what I really care about is the tens place that I get on the left and the right side. And the tens place that I get is A1 plus A2 plus Z, P1, V2, V1 plus P2, and B3. This is what I get on the left-hand side. And on the right-hand side, I get A1 plus A2 plus A3. And now I have a bunch of carries, but they come in a different order. So I would have carry coming from adding B2 and B3, and then the carry coming from adding B1 to that, B2 plus B3. And here I can cancel these A's out because for now I don't care about them. And I arrived at the following condition, which I'll call the carrying condition on this function Z. So the carrying condition is just what I got after I imposed the associativity condition, but just for our own sanity, the condition that we want is that if I add a 0, I do not want to carry anything. So this I'll call the normalization condition. So maybe NC or N for a normalization condition on my carry function. And then just on these sort of two very minimal restrictions, I would define a carry to be any function that satisfies these two things. I mean, recall that I do not care if there's a homomorphism or not. I just want this to be any random function that just satisfies these two conditions. And really, these two groups, together with my carry function, completely give us all information about E. In fact, there are many carry functions. So one remark that I forgot to make is that if I add two carries, I get another carry. So addition of two carries is also a carry. And this essentially follows by just the definition, right? Because if I have Z1 plus Z2 here, this identity is satisfied. And if I have Z1 plus Z2, this other identity is satisfied. And really, these three pieces of information give us all information that I can have about group E. So let's just for example, let's sort of work with the usual carry, which I'll denote by Z, and then consider the carry to Z. And the way this is going to work is that we will add normally, but instead, whenever we carry over a 2. So maybe if I do 37 plus 29 with respect to this new carry, I get 7 plus 9 is 16, but instead of carrying a 1, I would carry over a 2. And now I can just do 2 plus 3 plus 2, and that gives me 76. So the first question I can ask is like, oh, what group does this give us? So of course, this is a group with 100 elements because everything has a unique representation in terms of 2 digits, and there are 10 of each. So we have 4 options. So the structure theorem tells us that there are 4 options. I can have Z mod 100. I can have Z mod 50 plus Z mod 2. I can have, wait, did someone unmute themselves or was there a question? Okay, I'll pretend there was no question. I can have Z mod 25 plus Z mod 5, or I can have Z mod 10 plus Z mod 10. So let's see if we can eliminate some of these and really figure out what the group E is. So we notice, so the first observation is that the order of the element 0, 4 is 25. So you can sort of try to see that if you carry in this funny way, if you add 0, 4 to itself for 25 times, you get back 0. And this element has order 25. So we can eliminate, this should be Z mod 20. So we can eliminate this group and this group because they don't have any elements of order 25. And the second thing that I note is that there is no element of order 4. Like you'll have to play around with this a little bit to see that, to convince yourself that this is in fact true. And since there is no element of order 4, I can eliminate the group Z mod 100. And the group that I get with this carry operation is the group Z mod 50 plus Z mod 2. And just as an exercise to yourself, you can convince yourself that you can get all the groups, all the abelian groups of order 100. So try to figure out the carry function that gives you this group and try to figure out the carry function that gives you this other group. Okay, so now can we generalize this situation? I mean, it seems like there should be some way of generalizing this to not just restricting to Z mod 10, but also to look at more complicated groups. Like there's absolutely no reason we should only do carry operations, when we are adding two-digit numbers. So can we generalize this? And the answer to that will be yes, because if not, that would be a very anticlimactic end to this talk. Then you'll have the rest of your afternoon free. But the answer to that is yes, we can generalize it. And really what we are doing is that we are extending the operation on U and T by some function Z. So I will call an extension of U by T to be an abelian group such that T is sitting inside as a subgroup and U is the quotient of E by T. And similar to the observation that we had earlier, we can in fact show that in this setup, in the setup of an extension, any element X can be written uniquely as A and B, where A is what I'm calling my tens place, but this can really be arbitrary, and B will be in my group of units. And the way the proof will work is that we'll look at the projection from E to U, and I just need to define what this element means, and this I'll just call, I'll think of the symbol 0, B as being any element that just maps to B inside U. And I'll think of, for any A in T, I'll think of T sitting inside E as the element A and 0. And if I have these two things, and I start with any arbitrary X, the units digit of X, I should put that in quotes, units digit of X is just whatever I get after I project it down to the group U. And once I have the units digit, I can in fact recover the tens digit. So the tens digit I can just define by just looking at X minus the units digit. So X minus 0B. And you can sort of see that this sort of gives you some unique things. And so by a counting argument, I'll not write that down. So by a counting argument, you can in fact see that this decomposition is unique. Okay, and really, if we have such an extension, we get a carrying function for free, which is defined by this formula. I just add two things in the units place, and that gives me, like whatever carry I get, I define my carrying function that way. And somehow this completely tells us the addition operation on E. So this tells us about the addition operation on E. Okay. So on the other hand, if we do not want to start with an extension, if we start with an arbitrary carry function, and I start with these groups, then the set of symbols AB, where A is in my tens place and B is in their units, is in fact an abelian group. And the proof is very straightforward because the normalization condition tells us that identities exist, that we have an identity, we have a group identity, and this would be the element 0, 0. The inverse of an element I can explicitly write down in terms of the carry operation that I have and in terms of inverses inside my groups Z and T. So this is B comma minus B, and here I have minus B. And you can see that if you add this to AB, you in fact get the identity back. And associativity follows. So the carrying condition gives us associativity, because that's how we define the carrying function, such that carrying condition such that associativity works. And finally, commutativity also follows from like a somewhat annoying computation, but as long as you check that the carries are the same, that the carries commute, then my group operation also commutes. Okay, so what we have seen is that there is an extension that gives us a carry, and if I have a carry, I also get like some extension of groups. So this will, in fact, define like whatever group structure there is. This will define sort of a group extension in the sense that sort of in this sense. Okay, so the next thing that I want to do is to see when two of these things are define the same structure. So if I have two group extensions and I have a homomorphism between them, what is the right notion of an isomorphism between these two extensions? So the first thing that I want is that I want this to restrict to the identity on T. So I do not want my tens place digits to change under this homomorphism. And I want the induced map that is going from the quotient U to the quotient of E prime by T, which is also U, to also be like just the identity map on U. So this is also the identity map on U, is also the identity on U. And now we can ask that, oh, if I have such, like if I have a group homomorphism that satisfies these two conditions, what value should it take? I mean, of course, if on the tens place, I don't have much choice because I must restrict to the identity. So for a tens place, I'll have to write down A and 0. Similarly, on the units place, I don't have much choice. So I'll have to send those to just my usual units. But now if I have like two, like just any digits, like any 2-digit number in this setup, I'm forced to send B to itself, but now I can maybe add something to my tens place. And this addition will depend on whatever this units digit is. So this addition is happening from some map that is going from U to T. And note that these two conditions force us to send 0 to 0. So we can't start with any map that is going from U to T. We must start with a map that is sending 0 to 0. So that is great. But of course, I mean, the last thing that we want is that we want this map to, in fact, be a group homomorphism. And if you recall from your algebra class, the correct condition is that if I'm doing addition inside, that should correspond to addition outside. So this addition is happening in E, and this addition is happening in E prime. So if I write down the definition, so if I treat this as the definition of my function and I expand it out, and then I look at the tens place, the exact condition that I get on the left-hand side is that A1 plus A2 plus the carry that I get from B1 and B2. And note that this is the carry happening on the left-hand side. So this is the carry that's happening in the group E. And now I should have H of B1 plus B2. And if I compare this to the units, to the tens digit that I get on the right-hand side, I will get A1 plus A2 plus H of B1 plus H of B2. And now I need to carry, but now I'm carrying in the group E prime. So this will be maybe Z prime of B1, B2. And as before, as we did in the associativity condition, I can kill off A1 and A2 and end up with just this one condition on the carry. So really what we get here, and I'll just write it down, that this just tells us that Z of B1, B2 minus Z prime of B1, B2 should be equal to H of B1 minus h of b1 plus b2 plus h of b2. So really, if I want to have an isomorphism of extensions, this is a condition that it must sort of satisfy. I can write it down as a proposition. So because this essentially is a proof for this, is that if I have two extensions and I have their respective carries, and h is some function that satisfies these two things, then E is isomorphic to E prime as extensions, because that's how I went with this. Like we ensured that this is the identity, and we ensured that this is in fact a group homomorphism. So for this to be an isomorphism of extensions, it should come from a function of this form. So really what we are doing is that we are starting with a function that is sending 0 to 0, and we are measuring the impact this function has on the carries. So the impact this function has is whatever condition is on the right-hand side, which I explicitly write it down here. And just to carry the theme of naming things after words in the German language, impact is Beeinflussung. So I will call this a Beeinfluss. Plus is any function that arises in this way. So any function that arises as the delta of some function u to t, I will call this a Beeinfluss, and later on we'll see if this has any relation to to my carry operations. So really what we have shown is that if I have, we haven't shown this, but if you run this process backwards, you see that if you have any isomorphism, then z minus z prime should be delta h from some h. And it suffices in this case to define what that h should be. And so if we define h to be, so we define h this way, we say that let's look at what happens to 0b, and if this goes to h of b, then I define this function h that way. And it is clear that h must take 0 to 0. So h takes 0 to 0 because I want this. I know that this isomorphism indeed restricts to the identity on both of these digits. So h of 0, in fact, goes to 0. And now we can just compute. And now we can just check that z minus z prime is delta h, where delta h is defined in this way. So this is, again, a very quick computation that you can do. Just explicitly write down, you expand the definitions, and then we are happy. So what we have shown in this two ways, so first, this proves one direction, and this proves the other direction, is that two extensions are isomorphic if and only if their carries differ by one of these impacts. So if z minus z prime is delta h for some h, and this satisfies the usual conditions that we want it to satisfy. Okay, any questions so far? Because I think now we are, I don't know, I think we have built up enough random things, so in case there are any questions, I think it's good to. Okay. Okay, I thought someone unmuted themselves, but it seems that they have not. Okay, so anyway, so this is the theorem that we have, but now we can maybe formalize this a bit more, because it seems that if we start with the carries and mod out with this Beeinflussungen, we should get like some nice group structure, and maybe that will completely tell us what are the isomorphism classes of extensions. So let's define two groups. Let z of u comma t be the group of all the be the set, a priori just the set of all carries, and let b be the set of all these Beeinflussungen, which is just functions that arise by taking delta on them. And again, delta is this operation that I defined. So it just takes the first one, subtracts from that the sum of the two things, and then it adds b2 as the value of b2 there. So So this is my set B. And the first observation is that these two things are in fact abelian groups. And the second observation is that all the B's inside actually sit inside the group of carries. And the proof for this is not too bad. The first one just follows by checking that a sum of two carries is again a carry and that a difference of carries is a carry. But that is very obvious because if you add a carry to another carry, it satisfies the required conditions. And the zero carry is the identity operation. So that ensures that Z of U comma T is a group. And similarly, B of U comma T is also a group because again, you can just do a direct computation. So you pick some delta H and then use this and just check that this satisfies the two carrying conditions. So the carrying condition and the normalization condition. So the proof here is just a direct computation. Computation. And now, if we so since I see a Z and a B, maybe it is fair to call their quotient H. So H of U comma T, I would let this be the group Z of U comma T mod out by B of U comma T. So if this is the case, then our earlier criteria of two extensions being isomorphic is the same as saying that any extension is essentially characterized by this group. So any element in this group will give us like an extension, and any two extensions that vary by this difference in carries will in fact be the same element in this group H. Okay, so this is somehow the end of what I wanted to talk about. But I think before I close, I think it is only fair if I stop lying about what I'm saying and tell you what these things really are. The group that I was calling the group of carries is the group of cocycles, and these impacts or the Beeinflussungen are called the group of coboundaries. And really the group that we computed as a quotient is the second cohomology group of U with scalars and T. And this has, like classically, like historically, this is one of the first definitions of this group cohomology, like the second cohomology group of U with scalars and T. I think it's dating back to the 1930s, where they classified it in terms of extensions. But of course, there are more modern ways you can think of this. There's you can think of this as some funny X group and show that that is in fact isomorphic to the group of extensions that we have recovered. And you can relax some of the assumptions that we made. You can relax the assumption that E be abelian. You can relax the assumption that like my target group also be that my group of units be abelian and so on. And then you will get like the actual, you can follow essentially the same proof. Like if you look at a textbook, you can follow essentially the same proof and get that is the group of extensions in that case. So my only reference for this entire talk is this one paper that is called A Cohomological Viewpoint on Elementary School Arithmetic, and of course the usual sort of textbooks on algebra. So yeah, I see this is 40. This is a very good time to stop. This is roughly 40. And if there are any questions, I'd be happy to answer them.
Let's first thank the speaker. Yeah, are there any questions for?
Oh, I should mention I'm by no means an expert in group cohomology, so I think I will not be able to answer your very technical
questions. Are you an
questions.
expert in arithmetic?
I try to be. I try to add sometimes.
So I guess one small question is, so we did this with units and tens digits. Like how much more complicated does it get if you add like the hundreds digit into the mix? Oh, you just yeah, you can you can do like an extension on the extension. Then you can do z mod 10 and then try to extend it by z mod 100 that you get from this business.
So you can like do it twice, and then you'll have to carry twice, and it becomes more complicated, but you can do it.
And what like object you get at the end? Is it still like the second cohomology group or something else?
That will be the second cohomology group, but of a different group,
Okay.
with the different scalars. But it will be the second cohomology group.
Okay. Thank you. Yeah.
Yeah, I guess like usually the way I've seen like group cohomology, like you don't include those normalization conditions, but like I guess like it's fine if you do, like it doesn't really change the result.
I mean, you want, so at least in this exposition, I wanted 0 to go to 0, because that's one thing that gives us the identity later on. So this normalization condition ensures that when we make a group out of the set of symbols A comma B, I in fact have an identity in that group. Like if you just had this condition, it's not immediate that you'll have an identity in that group.
I mean, you also have a normalization condition for H. So, like,
Right, but the normalization condition for H, we kind of got it in a backwards way because we wanted this phi to be an isomorphism, and therefore it should restrict to the identity on both of these cases, and that forces you to have H of 0 to be 0. Oh, and also in general extensions, you want the identity to go to the identity before you take, the del or the delta.
Any other questions, comments? Not, let's think of it again.